Welcome to this next video in the playlist on complex analysis. In this video we're going to study the Cauchy-Riemann equations, which are conditions for a complex function to be complex differentiable. However, as we'll see, they are necessary conditions, but they are not sufficient conditions. So if a function doesn't obey the Cauchy-Riemann equations, you can then it's then the case that that function is not going to be complex differentiable. However, if a function does obey the Cauchy-Riemann equations, it isn't necessarily the case that that function will be complex differentiable. We'll see that a further criteria needs to be met in order for that to be the case. So they are necessary conditions for a function to be complex differentiable, but they are not sufficient alone to make that function complex differentiable. So let's derive these conditions then. So we'll be working then with a complex function, f, which maps the complex plane onto the complex plane. Let's just draw our planes ready for later. So here is our domain, and here is our codomain over here. And let's just remind ourselves of the definition of the complex derivative. So remember, complex derivative f prime of the function is defined as the limit as h approaches 0 of the complex function evaluated at z plus h minus the function evaluated at z divided by that complex number, that incremental complex number h. And remember that this limit here is a complex limit, so it's a limit that approaches the point from all directions. H is not just a real number now, it's a complex number. So what we're doing is we're going to a point, let's say an arbitrary point z here, and we're then imagining letting h vary over the entire complex plane. So if you like, we draw another picture down here where this complex plane is representing the h value. So h can vary over the entire complex plane. You can't let h equal 0 because this isn't defined when h is equal to 0, but every other complex number you can work out what this is. And then the derivative is not the derivative, but this quotient that forms part of the derivative here is then effectively a function mapping h onto the plane of complex numbers, so it itself is a complex function, and then we're taking the limit of that function as h approaches 0. So we can't work out what the value of the function is at h is equal to 0, but we can ask, can we take the limit? And if that limit exists, then we call that the derivative for the point z. So you imagine doing that then for every single point of the domain here, and you can work out then what the derivative is, and that then is a function from this complex plane to another complex plane. It's another function, which we call the derivative of our original function f. So importantly, remember that this limit then is a complex limit, so we're asking, does it converge from all directions, not just one dimension now, it's a two-dimensional limit. So, criteria then for that to be true. So in order for this limit to exist, it has to be the case that whatever direction you come in and take this quotient, it has to converge on the same thing. So why don't we just try working this out for one dimension and then do it for another one dimension? For instance, we could do it for the real and imaginary axes, and that's exactly what we're going to do, and then see what conditions we might get from setting the two equal to each other, and that is where you get the Cauchy-Riemann equations. Now, this derivation that we're about to do, it's an incredibly intuitive thing to do. However, if you actually examine rigorously what we are doing, it gets a little bit fiddly because we're continuously moving between different functions where the domain and the codomain are continuously changing. We're going backwards and forwards from complex numbers to real numbers to vector spaces, and we're having all sorts of different types of limits between different domains and codomains. So rigorously it does get a little bit fiddly if you try and keep track of what we're doing, but we're going to try and at least try to keep track of what we're doing. But as I say, this isn't difficult, this derivation. It is very intuitive. It's just when you actually look at what we're actually doing rigorously, it is a little bit fiddly. So let me try and explain to you. I'll do this nice and slowly. So, what we're going to do again is we're going to go to our arbitrary point, but this time, rather than taking a two-dimensional limit, we're going to imagine just taking a one-dimensional limit. So we're going to imagine just varying our complex number in one dimension now, and we're going to pick the sensible dimensions to use, which are the lines parallel to the real and imaginary axes. So we'll start off by doing the real one first, so we'll vary it in the real line here, and we're going to then take a one-dimensional limit along that line and see what answer we get for the derivative effectively in that direction, and then we're going to do it along the imaginary line, and then we're going to say these two need to be equal to each other if it's going to be true that from all directions it converges on the same thing, and then we're going to see what conditions we get out of that. So let's start then with the real one here. So rigorously, what we are now imagining doing, exactly equivalently to what we did down here, is we're going to imagine having, whoops, let me go back to the blue pen. So we're going to imagine having our h here. Now h is only going to be a real number. It's going to vary in one dimension, not two dimensions. And we're going to imagine then having a function from h to this quotient here, which of course is going to be a complex number. So it's going to be effectively imagining a function from the real line to the complex plane, and then we're going to take the limit of that function as h approaches 0. So again, we can't work it out when h is equal to 0, but we can say, does this limit exist in the one-dimensional sense as h converges on 0? And this is why I say that this gets a little bit fiddly if you try and think about it rigorously, because we have not rigorously defined how to take a limit for a function from R to the complex plane. However, I hope that this is intuitively obvious to you. What you can quite easily take our definition of limits from R to R, and we've also studied it from C to C, and you can work out what it's going to be from R to C. It's going to be that whatever epsilon ball you take around the limit, you want to have a delta interval around the point in the domain, such that all the points in that delta interval are mapped into the epsilon ball in the codomain, except the point itself. So if we're going to take the limit as h approaches 0, and we're going to, and let's suppose that limit exists and it's some complex number L over here, then we want it to be the case that whatever open ball, and I haven't actually drawn an open ball, I should have dashed lines, whatever open ball you take around that complex number in the codomain here, it should be the case that there exists a delta interval, because we can't have delta balls here because it's only a one-dimensional structure, but we can have the equivalent, which is a delta interval, an open interval around the point h, such that all the points in the delta interval are mapped into the epsilon ball, except the point itself. The point h itself, the point 0 itself doesn't have to be mapped in there. And hopefully that's intuitively obvious. Again, that's just saying that as you get closer and closer and closer to the limit, you have to be able to find an open interval in the domain such that all of those points are as close as that. That's what we're saying. We're saying that we want to be able to get arbitrarily close to this point L as we get closer and closer to the point around which we're taking the limit. We want it to be the case that as you converge down on the limit, all the points get arbitrarily close to the limit. That's all that definition is saying. So hopefully that's intuitively obvious to you. But this is why it gets a bit fiddly, because we're going to have lots of examples like this where we're taking limits in scenarios that we haven't rigorously defined it for, but hopefully it's intuitively obvious. Anyone who's studied topology or metric spaces knows that you can generalize the concept of a limit to any function between two metric spaces, or indeed more purely between any two topological spaces, and indeed both of these are very easily equipped with a metric, a very obvious metric, and they have topologies as well. When we're drawing them as two-dimensional planes and one-dimensional lines, we're intuitively thinking about them having actually certainly a topology, but really we're thinking about them having a metric. Every time we draw the complex plane, we're imagining it with a metric, even though we haven't rigorously given it a metric, and nothing that we've actually done requires it to have a metric. Every time we draw it like this to get this intuitive picture, we're really drawing it with a metric structure, i.e. a notion of length and shape and scale. Okay, so what are we doing then? So we're trying to take the complex derivative, and we're still trying to take a complex derivative, remember. We're not taking a real derivative, it's just we're doing it now in one dimension. So let's think about what we're going to do here. Oh, and we're going to, final little point, we're going to think about the function in its real and imaginary components. So we're going to split it down into its real and imaginary components, u of xy plus I v of xy. And that's really useful because remember both of these functions here, the u of xy and the v of xy, these are the component functions that you would have if we were taking the equivalent function to f in vector calculus, and also each of these independently is just a real valued function of R2, which we can draw a graphical representation of if we'd like to. So it's very, very useful to work with the real and imaginary components of the function, and indeed we're going to do that when we come up with the Cauchy-Riemann equations. So I'll actually go upwards, I think, rather than downwards. In fact, I should have gone upwards beforehand, because that's actually quite a good thing to do, because this is the bit that I like working with of the screen, and by moving it downwards we keep it on the screen without... Whereas if we were moving it upwards, we'd lose it. So actually moving downward, working upwards is actually quite a good idea. So let's do this then. So let's work out what the derivative is going to be along the real axis then. So we're going to take our function, and we're going to take it in real and imaginary components. So we're going to add on h to the x, like so. So we're going to get u at x plus h y plus I v of x plus h y, like so. So that's our complex function, the real and imaginary components of the complex function evaluated at the point z, which is xy, and I should just write that on the picture here. So this point z is just the point with components xy, so it's x plus iy. And we've now gone forward in the x direction by this amount h, a certain amount h, and we've got this. And then we're just going to subtract off what it was at the original point. So what it was at the original point was u at xy plus I v at xy. And then we're going to divide that whole thing. That's the difference between them. We're going to divide it by the complex number that we made the change, but that is just h. And that's the crucial bit here. Because we're only changing it by a real number, we're only dividing it now by a real number, and then we're going to take the limit as h approaches 0. And that limit is in the sense that we've just talked about, because h is varying over the real line here, and this therefore is a function from the real line to the complex plane, and we're therefore taking a limit, a one-dimensional limit of a function that goes into a two-dimensional space. So let's just rearrange this slightly. So this is going to get down to, we're going to group the real and imaginary parts together. It's the limit as h approaches 0, and then we're going to want to group this term with this term, and this term with this term. Now, I'm also going to separate this a little bit more. Again, this is something that we have not proven rigorously, but hopefully it is intuitive. If you have the limit of something plus something else, that is the same as the limit of one thing plus the limit of the other thing. As you get close, because remember what a limit intuitively means. It means as we get closer and closer and closer to this, so as h converges to 0, what does the sum of these things converge to? Well, hopefully it's intuitively obvious to you that that's going to be what one of them converges to plus what the other one converges to. If this is converging on something and this is converging on something, then when you add them together, they're going to converge on the sum of those two limits. So that we haven't rigorously proven that. It's very easy to rigorously prove that, but hopefully that's intuitively obvious, so we're just going to use that fact. So u at x plus h, and hopefully everyone has studied real analysis, where I'm sure your professors will have rigorously proven that limit of a plus b is the limit of a plus the limit of b. So the same sort of ideas that go into rigorously proving it there would go into rigorously proving it here. So we're going to split the limit as well. So limit as the limit of u at x plus h y minus u at x and y divided by h, that's 1, plus limit as h approaches 0. And in fact, we're going to pull out the I as well. I is just a constant, it's not varying, so we can pull it out to the front of the limit, plus I times the limit of v at x plus h y minus v at x y over h. Like so. Now look what we have here. These, remember, are nice functions. These are functions from R2 to R. Each of these components, the real and imaginary component functions, remember those are functions from R2 to R. Therefore, when we take a derivative of this form, what we're effectively now doing is taking the partial derivatives of those functions there. It's simplified it hugely. So remember, when you take partial derivatives back in multivariable calculus, what we would be dealing with is, let's study one of these functions and draw it nicely. So here is R2, here, and this is the codomain here, and we might be studying the function u here. So we have a point x, y, and every point in the R2 plane, or that should be R2, not R. So every point in here is being mapped onto a real number there, and we could draw a three-dimensional graph to represent this nicely. Now, when we take partial derivatives, what we do is we say, okay, if we're taking the partial derivative in the x direction, we say we're going to just vary in the x direction. So again, you can imagine having an h down here, a one-dimensional plane, which is our h. H is varying over the one-dimensional plane, and then we're going to get a derivative. Well, when we work out this quotient function, like this, for instance, u at x plus h, y minus u at x, y over h, we're effectively going to get a function from R to R, and then we're back to one-dimensional calculus, taking limits of functions from R to R, and we want to know, does this function does this quotient converge on anything as h converges to 0? And if it does, that's going to be the partial derivative at that point, xy. That is what we're doing here. We're just taking the partial derivative of this real component of our complex function with respect to x. That's all that becomes. So hopefully you can see that this equation is quite simply going to become del u del x, and remember, we're thinking of u as being the real component of our complex function, which we can then think of as a multivariable calculus function from R2 to R, plus I del v del x. So that then is the value of the complex derivative. That is a complex number. That would be the value of the complex derivative at our point z if we were just working it out in the x direction, but we know that if it exists, it is the same in all directions, so that would be the value that we need it to be in every direction if it is going to exist at a point. So now what we're going to do is do the same thing, but along the imaginary axis this time, and there is a subtlety here, because we need to remember not just to divide through by h this time, but to divide through by IH. And we're going to get another formula, and then we're going to set these two equal to each other, and that's where the Cauchy-Riemann equations come from. So let's do this again. So we want to now take the complex derivative in the imaginary direction. So again, we're going to imagine having a little h, but this time we're going to move by hi, and we're going to let h vary in the real plane. So what we're going to get this time, and I'll do it in a different colour, let's do it in green. So we're going to get the limit as h approaches 0, and then we're going to vary our complex function in the y direction by h this time. So u at x, y plus h plus I v x, y plus h. So that's just the value of the complex function at our new point, x plus I, y plus h. And then we're going to take away the original value, u, x, y, plus I, v evaluated at xy. like so. And then this is the crucial bit, because you might be tempted just to divide through by h, but that would be incorrect if you do that. Remember, we are taking a complex derivative. These are complex numbers up here. Yes, they're in real and imaginary components, so it looks deceptively uncomplex, but we are still trying to take a complex derivative, so we therefore need to divide through by IH, not just h, because we have to divide through by the actual complex number that we have changed by, and that complex number is IH. So yes, even though this limit now is just a limit in one dimension, it's varying over r, we need to make sure that when we actually take this value, the complex number that this quotient is representing, that it actually is the correct quotient for the complex derivative. And at the moment, this is the correct quotient for the complex derivative. We have our complex number at this point x plus, and I just want to write this down, this is the value of the function at x plus I y plus h, in brackets importantly. It's not iy plus h, it's iy plus ih if we expanded those brackets. This is the complex function value at the original point, and then we have divided through by the change, the complex number we have changed by. Right, so let's now do the equivalent thing here. So again, what we need to do is we need to group terms together. So we're going to separate the u terms and the v terms. And again, even though we haven't rigorously proven this, we're going to split the limit up into two separate things, like so. So, firstly, the u terms. So limit as h approaches 0. And we're going to pull out the 1 over I. So we'll bring out 1 over I over here. And then we're going to get u at x, y plus h, minus u x, y, all divided by h. And then we're going to get plus. Now, for the v terms have all got I in front of them, so the I is going to cancel, so we're not going to get the 1 over I this time, so we're just going to get the limit as h approaches 0 of v at x, y plus h, minus v x, y over h. And again, you can see we now just think of those functions u of x and y and v of x and y as the multivariable calculus functions, and then we're just taking partial derivatives, this time with respect to y. Remember, h, we were just imagining that as a real number. This is a limit, a one-dimensional limit, so these truly are just partial derivatives. So we then get, going over here, we get 1 over I times the partial derivative of u with respect to y plus the partial derivative of v with respect to y. Now, we can simplify that by multiplying top and bottom here by I, so then we get that that is negative I. So this becomes negative I del u del y plus del v del y. And I'm sorry that the u and the v look very alike, so let me just change that slightly. Del v, that's the del v, and this is the del u. So that is what the derivative, the complex derivative, is going to equal if you take it in the imaginary axis. But of course, if the complex derivative is going to exist, then this has to equal this. So we have a, remember these partial derivatives, these are just real numbers. So this is the real component, this is the imaginary component here, this is the imaginary component here, and this is the real component. So if they're equal, we can now just set real and imaginary components equal to one another, so we then get that, and I'll write this in red. These are the Cauchy-Riemann equations. The partial derivative of u with respect to x has to be equal to the partial derivative of v with respect to y. Think of what that means. U is the real component of the function. When we take the partial derivative of that with respect to the real axis, it has to equal the partial derivative of the imaginary component of the function with respect to the imaginary axis. And then the other Cauchy-Riemann equation is that del v del x, so when you differentiate the imaginary component of the function with respect to the real axis, it has to equal negative of the real component of the function differentiated with respect to the imaginary axis. Those two equations there, and I'll put a box around them, those are the Cauchy-Riemann equations. And they are a way for you to check whether a function has any hope at all of being complex differentiable. So if you have some complex function written in real and imaginary components, u of xy plus I v of xy, you can work out the values of these partial derivatives. You just take these components, which are viewable as multivariable calculus functions. You take the partial derivatives in the way that you would, in the way that you've been taught in multivariable calculus, and then work out their values at a point. If these equations are satisfied, then there is a chance that the function could be complex differentiable at that point. If the equations are not satisfied, then that function is not complex differentiable at that point. So they are an excellent way of proving that a function is not complex differentiable at a certain point. However, alone, even if they're true, it doesn't mean necessarily that the complex function is differentiable at that point. And the reason is, hopefully, quite obvious. All we have done is differentiate it in two directions, the x direction and the y direction, and we've said they need to be equal to one another if the function is going to be complex differentiable. But even if they are equal to one another, that doesn't prove that whatever other direction you go in, it's going to be the same. What about this direction, for instance? The 45-degree line. What about that direction? That direction could be something completely different to this direction and this direction. So this direction and this direction being equal to one another is what those equations say. It doesn't prove that it's going to be equal to what it would be equal to if you took it in this direction. So alone, the Cauchy-Riemann equations do not prove that a function is complex differentiable. However, they are useful for proving that a function is not complex differentiable, because if they aren't satisfied, it categorically isn't complex differentiable at that point. So they are therefore necessary, they have to be true for it to be complex differentiable, but they are not sufficient because alone they are not enough to mean that it is complex differentiable at that point. We'll have a break here, and in the next video we will see how we can add another condition, and if that other condition is met, then the function will be complex differentiable at that point.